I'm Alex BOGGESS.
I'm Julie Davenport.
Michael DEFRANCESCO.
I'm ZACK ORBACH.
I'm Michael Pierce, and this is the Modular and Scalable Scale Car Platform and Performance Testing Systems for Mechatronics Systems Research, MQP.
Advances in mechatronic system design, such as autonomous navigation, rely heavily on the availability of robust mobile platforms. Through this project, a scalable, modular, and open-source mobile scale car platform was developed. Commercially available cars exist, such as Lego, BEGGESS, and Turtlebot. However, these options are either high in cost or do not have the modularity and robustness that is needed. Our car is both low cost to manufacture, has modular components that can be integrated, and is robust.
In order to make our car robust enough to successfully integrate self-driving capabilities and to have comparably scaled abilities as actual cars, we developed the following specs for our car. The chassis must support the full weight of all components, including a control moment gyroscope assembly. The independent suspension system must be able to go over a 1-inch bump smoothly and pass a fatigue test designed by the team. The output torque of the transmission system will be large enough to propel the car up a 30-degree inclined ramp. The steering system will have a minimum turning angle of 30 degrees on each side, and that the steering linkage will pass a fatigue test designed by the team.
The steering system is a parallelogram system composed of 6 links designed to accommodate the independent front suspension. It has a maximum turning angle of 41.94 degrees and a turning radius of 1.55 feet, allowing for tight turns. A steering fatigue test fixture was made that continuously turns the wheels of the car back and forth. Using the fatigue test, we were able to determine the car could turn 3,000 times consecutively before the servo strained greatly. Additionally, we were able to use the test rig and tracker software to get the velocity and acceleration values needed in order to experimentally determine the torque required to turn the wheels.
The 14.14 by 8.75 inch chassis was designed to withstand the weight of the components, including the 2.344 pound CMG. Since the overall size of the chassis exceeded our 3D printing area, the chassis was cut into 2 pieces, then epoxied together. There are also slots in the bottom for zinc rods, which allow for a more structurally stable chassis. The chassis has mounting locations for each of our subsystems and is designed for ease of interchanging modular subcomponents. The independent suspension system was developed to keep the chassis of the vehicle as stable as possible. The suspension keeps the wheels on the ground to maintain traction through bumps and turns. The 4-bar parallelogram was designed to allow lateral travel while keeping the wheel horizontal. On the lower linkage of our suspension, we've attached shock absorbers, which provide spring force as well as dampening of the vibrations using 50-weight shock oil. The front and rear suspension systems are nearly identical in design. The suspension is designed to handle 1-inch bumps and to withstand 7,000 cycles, verified via a modular test rig. The fatigue test fixture was designed with a cam to articulate the suspension over a certain amount of cycles.
Gearbox and differential are both off-the-shelf products. The Vex Robotics Planetary Gearbox has an interchangeable 5, 7, and 9 speed reduction, paired with the Traxxas differential that has a speed reduction of 2.85. The modularity of the gearbox allows for changing the speed and torque output of the car. This was accomplished by designing a custom differential housing and driveshaft couplers that allowed the gearbox to be easily exchanged. A dynamometer was made that can measure and test the output torque, wheel speed, and wheel RPM for each modular gearbox.
The team used standard metric hardware, M3 and M6 fasteners. Completing fastener analysis of all major systems in the car by hand and in MathCAD proved that the team's designs were structurally sound and no risk of failure. Analysis was performed on the CMG and top plate subsystem, the steering system, the suspension system. This was done to ensure the fasteners and moving systems would not strip or fail during use.
The CMG used in this project was designed by an MQP team during the 2018-2019 academic year. The output torque of the CMG is 6 Newton meters. The car has a top plate configuration mounted to the chassis that houses the CMG and the sensor box for the self-driving package. When used, the CMG did not produce enough torque to affect the movement of the car. To remedy this, the addition of another CMG will be explored in an upcoming project.
The car takes approximately 3 hours to assemble once all the parts are 3D printed. The parts that need to be 3D printed are open-sourced for all to use and can be printed on any printer with a large enough bed. The parts that are not 3D printed can be found at any hobby store. By completing design of manufacturability and assembly analysis, we are able to verify that our car was designed well for manufacture and assembly. We only introduced extra pieces than the minimum necessary when it was needed to make 3D printing more feasible due to size or shape.
The platform the team developed exceeded the requirements set out. The car can traverse a 30-degree incline easily. The self-driving and sensor packages were successfully integrated, proving robustness. The CMG was integrated, however, it did not produce enough torque to perform rollover recovery for the car. Therefore, the future work for this project includes integrating a second CMG. The work accomplished will be used in ME 4322 and 4320 to help students understand mechatronic systems.